All right. I hope you followed the introductory lecture on Laplace transforms, because as I emailed you yesterday, we're going to finish today things about Laplace transform because they're too basic and useful only in very limited type of situations. So we need to keep moving. And for the remaining of the topics of the course, I haven't really decided, but my priority is going to be, out of the enormous list that we have to cover, to be topics that I think are essential. So there may be things that there's no way I can cover. So even the limited things we will cover will look intensive because the homeworks will be intensive, right? I need to be sure that there is a comprehensive set of problems so we can have a reasonable exam 3. By the way, because some of you asked me, there is no final exam, all right? So when we finish with exam 3, basically we are off for a happy Merry Christmas, okay? So there will be no final exam. You can plan your trips to anywhere, and et cetera, et cetera. Okay, so today we're going to continue with some applications of the Laplace transform. As we know, it is relevant for solving initial value problems that have discontinuous forces on them, because the techniques we used in earlier lectures don't actually work for this type of problems. So what do I mean, a discontinuous problem? So you can think of an initial value problem where you specify the displacement and velocity, and the right-hand side, the forcing term, is, as you see here, is 0 for some time, then it jumps to 1, and then it jumps again to 0 after time 20, okay? So we would like to solve problems like that, and the Laplace transform is literally ideal to do this type of problems in a sort of a minimal effort, almost in a mechanized fashion, right? You don't need to memorize anything. You just, if you have the tables of Laplace transforms in front of you, this is what you need to use. I don't expect you to memorize anything because I don't memorize anything, okay? All right, so we need to be able to deal with problems like that. And by the way, the response for this system, if for some coefficients A, B, C, if you plug in this input, it looks this interesting thing. So you can see as the forcing jumps at time 5, the response suddenly jumps as well. Then there is some oscillations. Then suddenly it goes down because of this discontinuity in the forcing terms. And then in a damping oscillatory manner goes to 0 after a long time. So it would be nice to be able to actually get this behavior in an easy manner. All right, so I suppose you have already learned and worked on this in your homework on how to operate with step functions and shifted step functions. So the forcing term that you saw in the previous plot, I don't know if actually the plot comes again. Yeah, here it is. All right. So again, it is 0 up to 5, time 5, okay? 0 after time 20, and then it jumps between 5 and 20. So I write this as u5 of t minus u20 of t. Okay, so what is u5 of t? Since you read all the notes. It's a step function that starts at what time? At time 5, okay? So basically, you start with a unit step function at time 5, all right? And because you want to have 0 at time 20, you have to subtract a step function u20, okay? So this is sort of a compact way to write things. Literally, this is what we have, but you know, this looks nice, okay? There is really no other reason to use this notation but because it looks nice and it will allow us to use formulas for Laplace transform. All right, so we need to solve this problem. The idea here is we are going to assume that the Laplace transform of the derivatives exists. So you read the corresponding theorem in the early part of the notes on when that is the case. So we assume that we can take the Laplace transform of every term. So the Laplace transform of y double prime and y prime and y, And then we have the Laplace transforms of these shifted step functions that you see here, okay? And so I remind you, I just actually, because I don't memorize things and I want to be able to cover these things in the lecture in 10 seconds, I cut it and pasted all the formulas that we will need to use. So if we have the Laplace transform of a shifted step function, this is what the Laplace transform is. E to the minus cs divided by s, where c is the time that you do the shifting, right? So I gave you a table, but actually if you want, you can go to Wikipedia and download the front table that has the Laplace transform of every function that we need to use in this course. But we know how to compute the Laplace transform of this and the Laplace transform of that. Okay, so we expand the derivatives. And this you need to know, right? You don't need to memorize this. You just need to know the Laplace transform of the second derivative is s squared times the Laplace transform of y minus s y0 minus y prime of 0. And I remind you, the nice thing with the Laplace transform is that the initial conditions come directly in the Laplace transform. You don't really have to solve the problem in terms of some constants and then apply initial conditions. No, the initial conditions are taken care of directly in the Laplace transform, okay? And there was a factor 2 here that carries on. So this is the Laplace transform of the first derivative plus 2 times L of y equal to that. So if we put all of this together and we call capital Y the Laplace transform of what we need, we get, let me see if there is a better equation. So we get this nice equation. So now you say, I am stuck. What is that? All right? So immediately you can see that you have some things in the denominator, so you're going to have to use some partial fractions to see what type of function this 1 over s times 2s squared plus s plus 2 gives you. And then you see this term e to the minus something. And when you see e to the minus something, what does it remind you from another theorem in the first part of the lecture? When you have e to the minus 5s, what does it remind you? So if you multiply the Laplace transform by e to the minus cs, what happens to the function itself? There is what happens. So what happens? So when the Laplace transform is multiplied by e to the minus cs, what does that imply for the function? What is this notation? What is all of this means? So the Laplace transform of this is equal to that, right? And this is what we have here. So we have, if we call this 1 over the denominator h of s, leading to some function h of t, okay? That's my f here. And then I have e to the minus cs. So this is the function that gives you this Laplace transform. So what this function is about? Remind me. What is that function? With words, what is this function? I mean, I have a function f of t, so what is uc of t times f of t minus c? You have done the homework. Yes, please. Is the shifted step function. So effectively, actually, it's not the shifted just step function. Okay, it is the function f of t shifted in time by distance c. All right? And we use basically this step function uc of t to indicate that from 0 to c is 0. And then after that, basically, we have 1 times the shifted function. Okay, excellent. All right, so effectively, if we can compute the function that corresponds to this Laplace transform, we will be able to immediately write down what e to the minus 5s times h of s means, and it will mean some function, this function h of t, shifted by this distance 5 and distance 20 that we have there. All right, so that's the answer. If somehow we can compute the function h of t that has this Laplace transform, the solution is this, right? Is the function h shifted by distance 5, that's it, okay? Minus the function h shifted by a distance to 20. I'm mixing languages here. You know, I can, when my brain runs, I may start speaking French in a second, or Greek, or whatever, or Chinese for that matter, if I don't make any sense, okay? So that's the answer, okay? But we need to compute this function h. All right, so partial fractions, we're going to have to sort of decompose that 1 over something to 1 over little functions that somehow we can compute what the Laplace transform of those fractions will be. And I'm not going to do the algebra, but you can see here I decompose it to terms like 1 over s and 1 over 2s squared plus s plus 2. I trust that you can compute ABC, and there is the answer. And you may say, yeah, but that doesn't help me. Maybe I can find what the Laplace transform of 1 over s is, but I don't see what to do with this. So what are you going to do? What did you do in the homework when you had these terms? I mean, what's the idea, right? It's algebra, it's labor, but what's the idea? What would you like to do to that term to simplify it? What would be nice? I mean, we know the Laplace transform of the sines and the cosines, right? Things like, you know, alpha over s squared plus alpha squared, or s divided by s squared plus alpha squared. And we also know if we have the Laplace transform shifted by some distance, how to compute that. So what do we need to do here to simplify this? To write it like sines and cosines, or the Laplace transform of sines and cosines. So after some labor, this is what you need to do. So what have I done here? It says here, completing the square. So I want you to look at it and tell me, why did I do whatever algebra I have done to put it in that form? By the way, completing the square, hopefully you can appreciate what it means, right? Because we created of s plus something square. That's what that means. So what is the purpose? Why did we do these partial steps to write this as that? Do we know the Laplace, what the function is that has a Laplace transform s divided by s squared plus something? Plus something square, actually? What's the Laplace transform of that? I mean, what's the inverse Laplace transform? So s over s squared plus alpha squared is cosine. A over s squared plus alpha squared is sine of at, okay? But we have a problem here. I don't have s divided by s squared plus alpha squared. I have s plus 1/4. So what do we do? Again, you look at the tables, like, is there anything like that where I do some shifting? Or you look in the notes in the computer. All right, let me see what you're looking. Nice. Nice. Okay, so tell me, s plus 1/4, what do I do? What's the rule? How about that little thing there? If you have the Laplace transform with an argument s minus c, so if you shift s by c, what does that do to the time domain? You multiply by this exponential e to the ct, right? E to the ct. So if this s over s squared plus alpha squared is cosine of alpha t, this whole bracket here, what is it? Will be e to the what? Tell me exactly what this will be if s over s squared plus alpha squared leads to a cosine of this square root of t. Will be e of what? E to the minus negative 1/4 of t times the cosine of the square root of 15 over 16 of t. And there is the answer. All right, so the function h of t is this. And you remember, if we compute the function a of t, I indicated you already know, using the shifted responses, what the solution to the differential equation is. And here is the answer to the differential equation. If you try to do this with other methods, it may take you 2 hours of algebra here and there. With the Laplace transform, it's really trivial. You look at the tables, you extract the needed information, and that's what you need to have, okay? So again, this is the function h shifted with shifted time by 5, and the function h shifted by a time 20. And 5 and 20, you remember, were the interval where we put this external force equal to 1 in the first statement of the problem. Okay, so if I plot the solution, this is how it looks like, all right? So nice. Okay, so this is my nice function. Now, if you want to actually do this problem with the old techniques that we learned on solving linear initial value problems or ordinary differential equations, effectively you are going to have to solve 3 different problems, okay? So the first problem will be from the interval 0 to 5 with 0 external force, then from 5 to 20 with external force equal to 1, and then after 20 with external force equal to 0. And then you're going to have to match the initial conditions for each of these solutions, y1, y2, y3. So for this, you have your 0 initial conditions that the problem statement gave us. For y2, because this first problem will give you a 0 solution, right? There's nothing going on. So obviously, y2 at 5 and y2 at 5 will be also 0. And then for y3, all right, for y3, you're going to have to use continuity and take the displacement y3 and the derivative y3 prime to match those that you computed from the second problem, okay? But you can see this is a lengthy process. You're going to have to solve each of these equations together, match the initial conditions, and hope that at the end of the day you will get the right answer. And you will, right? So I am not going to actually, let me just jump all of these things. I don't really want to, I don't have time to do this type of things. Life is too short to be wasted with little things. Okay. So let me actually talk a little about the smoothness of the solution, okay? Can somebody remind me, because his 10 slides behind us, what was the differential equation looking like? It was like 2 times y double prime. Anybody from the notes? How does the equation look like? It was y double prime plus, let's say, y prime plus y equal to some g. And that g, remember, it was 0, then jumps to 1, then again jumps to 0, equal to 0. So here the statement says that the solution to the differential equation has, if we call it phi, right, that's the solution. Phi and phi prime says they're continuous at the points where the external force is discontinuous, but then it says phi double prime has a jump of 1/2 at time 5 and time 20. So can somebody give me some explanations of all of these things? So why phi double prime, the second derivative of the solution, has a jump? And by the way, this is related with one earlier homework problem that I asked you to transform basically the application of the delta function and write it down in terms of initial conditions. At least that's how the solution to the problem was given to you. So can somebody tell me why phi double prime has a discontinuity and it's equal to 1/2 at these 2 locations and minus 1/2? I remind you, the equation was 2y double prime plus y prime plus, let's say, y equal to g. And g had a discontinuity of 1 up and minus 1. So why the solution, the second derivative, has a jump of 1/2 at equal to 5? If you look at this equation, the right-hand side of the equation at equal to 5 is what? at t equal to 5, it jumps. So something in the differential equation needs to jump. And that something is the second derivative. And why do I say that the second derivative will jump by 1/2? Because the differential equation was of what form? It was 2 times y double prime equal, etc. to g, right? G is on the right-hand side. The differential equation had a 2 in front of the second derivative. So basically, in this type of problems, the highest derivative accounts for the discontinuity in the forcing term, right? And this is very typical on this type of application. So just in case, I may ask you, to say something about the regularity of the solution versus that of the forcing function. And I think the best way to do this is to look at the differential equation and get your conclusions from there. And you notice again, at t equal to 20, the discontinuity is minus 1/2 because g goes down by minus 1. So 2y double prime has to match that, so the discontinuity in y double prime will be minus 1/2. By the way, because I copied this plot here, this is a function g of t, right? So it should not be y equal to g of t. So it's the function g of t. Okay. We don't need this. This is I just stated. All right? So there is another example in the notes. So I'm going to bypass, actually, for now. So in case it comes back, we have time, somebody should remind me to do this example as well. But let me do slide 77, okay, I think, right? And we will discuss about impulse functions. And I'm going to assume that you're not strangers to the delta function. So I am not going to go and derive what a delta function is as the limit of this and that. I'm assuming you know. If you don't, you look at the slides. It's a fundamental function in everywhere in science and engineering. So first, in simple terms, what's a delta function concentrated at time 0? It's a function that goes to infinity. It's a spike that goes to infinity at time 0. And it's 0 everywhere else. However, because it goes to infinity, when you integrate that function from minus infinity to infinity, so literally when you integrate that function around 0, you get 1. Because the function is so big, right? So you get a measure that is not 0. I mean, any other function, if you integrate it around the discontinuity, even if the discontinuity is big, you will get an integral of 0, but with the delta function, you get an integral of 1. So if you want to visually see what a delta function is or from where it comes, you can think really that you have this step function between minus tau and tau, and the magnitude of this response is 1 over 2 times tau. So you can see if you take the area of this, right, would be 2 tau times 1 over 2 times tau, so you get 1. And as tau goes to 0, that's when you get the delta function. Okay? That's as much as I want you to know. Delta function, extremely important, okay? And you may say, but is it in life anything a delta function? Well, yes, everything. I mean, you can interpret everything as something happening now and something happening the next second. So the delta function, actually, the impulse response, can be used to give you the response of any other forcing term when we solve ordinary differential equations. And hopefully, I will have the time to show to you today. OK, so that's the delta function, all right? And if you take a delta function now that is centered around time t0, again, this spikes at t0, all right? But for any other time is 0. And when you integrate it from minus infinity to infinity, literally, the only measure you're going to get will be from t0 minus to t0 plus. The integral is always 1. And you can take this as the definition. You can take this as a common sense statement, all right? But this is extremely important, okay? What allows this integral to be equal to 1 is because this delta function at t0 goes to infinity. All right, the Laplace transform now of a delta function. All right? I am not going to do the derivation by taking that little step function that I had before and taking the limit as tau goes to 0. But I'm actually, you know what I'm going to do is, I'm going to go and put directly this delta function inside the integral there. Forget this limit, forget the proof here. If I put the delta function directly over there, you remember the delta function is everywhere 0 except at t0, all right? And there is something important here. When you convolute a delta function with any other function, what do you pick up at the end of the day when you do the integral? You pick up the value of the argument that you have here at t0. So what you're actually picking up is e to the minus s t0. Okay? This is extremely important. Extremely important. So again, if you plug in the delta function inside the definition of the Laplace transform, so if this was a delta function directly without doing this limiting process, okay, this integral becomes e to the minus s t0. Again, think that everywhere that delta function is 0, but at that location t0, all right, you remember the integral of the delta function gives you 1, but when you convolute it with another function, it gives you that function at that point, which is e to the minus st0. So what is the Laplace transform of an impulse function of delta of t at t0 equal to 0? So if I put an impulse at time 0, what's the Laplace transform of that, according to this derivation? What is the Laplace transform when I take delta of t? 1. So remember, when you see 1, all right, and 1 sounds trivial, but you know what? When you see 1 is the inverse Laplace transform of the delta function at time 0. All right. And what is the Laplace transform of this? If you have a delta function at t equal 10, is e to the minus what? 10 what? So e to the minus 10s, okay, all right. And this is what I mentioned before with the convolution, right? So again, you can actually follow the proof using the mean value theorem, or you can actually, sometimes in mathematics, when something looks good, it has to be right, all right, because mathematics don't lie, okay? Usually, one of the reasons I like typing things is when I look at them and it's like, this looks nice, then it has to be right, okay? So when you convolute the delta function with f of t, as I mentioned to you, you get f of t0, and that's what we used in the previous slide. Okay, so let's solve a problem with the delta function. So we're going to have this second order ordinary differential equation, and the impulse is basically a spike at time t equal to 5. So you can actually anticipate the solution. How does the solution will look like to a problem like this? Take a guess. So if you look at the homogeneous equation, obviously it has a damping coefficient, it has a spring there, but how will the solution to this problem look like? What do you think? So you put suddenly a spike, but the time t equal to 5. So what is going to happen before 5? How will the solution look like? What do you get before time 5? What do you get? Nothing. It's all about nothing. Okay, you get nothing. And what happens now at time 5? Obviously, something is going to spike because something in the differential equation needs to respond to this spike in the forcing term. And then, but it will spike only at time t equal to 5. And then what happens after t equal to 5? Whatever you get from that impulse, obviously is going to die down because there is damping involved in the differential equation. Can you see that? So really, if somebody asks you to plot the solution, I'll take 0, it spikes to something, and then I'm going to put some dying oscillation, and that's the answer. I don't have to solve this equation. I know what the answer is. Okay? So if you take the Laplace transform of the right-hand side here, will be e to the minus 5s. All right, so I plug in the initial conditions. I take them to be 0. So there is no driving force from the initial conditions. So we have to solve this nice, we have to find the inverse transform of this. So can you tell me what the steps will be to get the inverse transform of that? We did this in the previous example. So I see an e to the minus 5s. So what does that mean, e to the minus 5s? If we can compute the function that corresponds to 1 over 2 square s squared plus s plus 2, then what does the e to the minus 5s will do to that function? Shift it by 5, okay? Easy. So we need to identify what's the inverse transform of 1 over 2s squared plus s plus 2. And then again, the idea is to do partial fractions. And in this case, actually, you can just close the square. And if you close the square, that's the answer. By the way, this concept of close the square, it sounds like something you will say to elementary school kids, close the square. But it's a very fundamental concept, not just on this problem, but it comes, for example, it comes in probability problems, with Gaussians and, et cetera. But so there is a reason here that we say closing the square to be a fundamental process, right? We need to take advantage of the Laplace transform of sines and cosines. And obviously here we get the Laplace transform, we get a sine basically from this, but I see s plus 1, 4. So, so basically we have this last case, the s is shifted by minus 1, 4. So we're going to get e to the minus t over 4. So our function actually is going to be e to the minus t over 4 of sine of the square root of this t, and then that whole thing is going to shift by time 5. Can you see that? First, we have to deal with this, right? This looks like a sine. I see a 1/4 over there, so that 1/4 will multiply my function by e to the minus 1/4 t, and so I'm going to have e to the minus 1/4 t sine of that square root of t, and then the whole thing will have to shift in time by 5. So there is the answer. All right? If you, again, there is really, you need to just learn how to use the tables on doing this. All right? So you notice there is e to the minus t over 4 that I mentioned here coming. That's the 1/4. And then what do? We shift in time by 5, t minus 5, t minus 5. And that's it. And of course, we have to put a u5 there to be sure that the function is 0 before time t less than 5. And you told me that the solution will look like that. So really, getting this result hasn't added anything to my head because I already knew the solution has to look like that. So it's just algebra. If you know what the answers look like, that's more than 50% of the correct result. But don't try that in an exam. Okay? Only just for a lecture. Okay. I have a question now for you. So we, come on, where is it? So we plug in this delta function in, so you remember the differential equation. Actually, let me go back. So we computed the solution to this problem. Can you tell me what type of smoothness you anticipate for the solution to this differential equation? Is y going to be continuous? What part of the solution is going to be discontinuous? Look at the differential equation. How about the second derivative? What do you anticipate the second derivative at, looking at it, at the differential equation? What happens to the second derivative? I mean, I see there the second derivative has to match a delta function, and delta function goes to, blows up, right? So what about the second derivative then? I mean, I want to know if y is going to be continuous, and I want to know if y prime is going to be continuous, and I want to know if y double prime is going to be continuous. So what do you think? looking at the differential equation. I mean, if this is unbounded, something at time t equal to 5 has to be unbounded on the left-hand side. And what is that something? Y double prime, all right? And actually, for y prime, the fact that is, is going to be continuous, you can actually see this. If you integrate this equation from 5 minus to 5 plus, you're going to get 2 times y prime. This, you will get a y, and this, you will get the integral of y, which drops, and this drops. And then you will get 2 times y prime equal to the integral of this, and the integral of this around 5 is equal to 1. So y prime at 5 is going to do what? What's going to happen to y, to the derivative of y at time 5? You actually did this in your last homework, not this one, the previous one. You remember I was asking you to calculate the impulse response, right? And the delta function was a time 0 that you took, okay? And then you arranged the initial conditions to account for that. Or I hope you did that. At least I did that in the solution. So what happens to y prime at time 5? I mean, if I integrate this equation, I'm going to get a y prime here. I'm going to get 1 there. So what happens to y prime at time 5? What's the integral of y double prime? Y prime. So 2 times that y prime has to match what? Has to match the one that you get from the forcing term. So what happens to y prime? Say it again? 1/2, all right. So do you see here that the slope somehow changes suddenly? Do you see any slope change? At time 5, do you see any slope changing? I do see one, all right? Okay, all right, done. Again, you look at the differential equation to figure out what is, what's going on. Okay, so now, let me jump to slide 88, okay, to discuss about something that actually I gave you to do in the homework without the Laplace transform, the previous homework. I have no idea if anybody did it, but some of you read the solution. So, and this has to do about the convolution integral. So I'm actually going to jump a few things and go directly to what is needed. And what is needed, oh no, wrong. All right, so let me just put the whole theorem up. So let's suppose that we calculate, let's say, the solution of a system of a differential equation, and the response comes to be the product of the Laplace transform capital F of S and the Laplace transform G of S, okay? And let's say that the corresponding functions are F of t and G of t. So here we have basically the product of 2 Laplace transforms, all right? And the question is, if we know the function corresponding to capital F and the function corresponding to capital G, is the function that corresponds to their product is F of t times G of t? And the answer is not, all right? So if you have the product of 2 Laplace transforms, the corresponding function is not the product of F of t and G of t. The corresponding function is the convolution that you see in here. This theorem is extremely, extremely important, okay? Very relevant to everything, okay? So the idea again is, if F of t is the function corresponding to F of S, G of t the function corresponding to G of t, then the function corresponding to their product is this function h of t, which is, as you can see, it's the convolution. So I'm convoluting f and g, all right? This is my kernel function. And you can actually reverse the role of f and g. These two integrals are the same. They're identical, okay? So, and the convolution is like a product, but it's a different type of product that we denote depending what books you read. Let's say f star times g, all right? But the key idea here is if I multiply the Laplace transforms, the functions don't multiply, they convolute, okay? This is the fundamental theorem. Now, you may ask me, this sounds like a very serious theorem. Can you actually prove it? Yes, I can prove it in one slide, but I don't have time, okay? The proof is actually given on this slide, and it is literally, when I look at it, the proof is very fundamental to many, many problems you will see in many different courses, because you have to do this proof for sort of different cases. I'm only going to tell you what the idea is, right? You're going to take the product of the Laplace transform of S and G of S, and somehow manage to write this as the integral from 0 to infinity of e to the minus st times this convolution function. And then immediately you know that the function that has a Laplace transform f times g is this convolution. And what do you need to do in this little derivation on this slide? You have to use one trick, okay, that goes as follows. I'm going to tell you the trick, but I will not explain to you how it comes in the steps, because you can read it. It takes, just a few, a minute or so to understand what's going on. But here's the idea. If you want to calculate, if you have two variables, and I call these variables t and tau, and you want to integrate below the line t equal to tau, all right, this darkened area that you see, there is two ways to do the integration. One way is to take a time tau, all right, that's this horizontal line, and integrate on every strip from tau to infinity. So you integrate on t. And the other way to do it is to pick up a particular time t, and then integrate vertically from tau equals 0 to tau equal to t. So when you change the way you do the integration, this leads to this nice convolution and proof of this convolution theorem of the Laplace transform. Okay? So there's really, it's simple, one change of variables, and the rest is playing with integrals. And rather than integrate vertically, you integrate horizontally, but in both times you get this shaded area. The magic of mathematics, if something looks good, it has to be right, okay? So let me leave it there. But I mentioned that this is very fundamental, and you'll be surprised that it comes up in many different areas, okay? I'm going to explain to you after the class, okay? So hold on there, okay? All right, so let me do one example, right? So if you have, let's say, you want to find the function corresponding to this, okay? So you can actually split this as 1 over s squared and a over s squared plus a squared. Obviously, the Laplace transform, the function corresponding to this is a sine of at. This is a time t. So obviously, you're going to have to take a convolution, and that's the right answer. So the right answer that leads to this Laplace transform is the convolution of t with the sine of alpha t, okay? And actually, if you do integration by parts, and I think it's on the next slide, you can, with some algebra, you can actually simplify this and write this explicitly with this nice formula. All right, so basically this whole integral, you can simplify it and directly, I'm sorry, h of t, yeah, you can take this nice form. Let me see if we should do this. Yeah, so let me do this. I'm going to need to do only one example and relate this to the homework problem that you did with the impulse function. Somewhere, if I remember, I asked you to figure out what's the relation of the impulse response with the step response. You remember that in one homework? So I would like to to give an answer to that using the Laplace transform. So let's say we have a differential equation that involves this, okay? And G can be any function right now. We don't really care. G can be anything. And we have some initial conditions. Take the Laplace transforms. We just write a Laplace transform of G as capital of G, okay? So we get something like that. And if I rearrange it, I get the Laplace transform of the solution. Has two components. One is 3s minus 1 divided by s squared plus 4. And another one is gs s squared plus 4. Pay attention now that 3s minus 1 s squared plus 4, it actually does not involve the right-hand side at all. This is the only term that has the right-hand side, okay? So literally, if you take, so this term actually not only does not involve the right-hand side, but it involves the initial conditions from what I see. So can you guess, if you take the inverse transform of 3s minus 1 divided by s squared plus 4, you're going to get the solution of what problem? So it does not involve the right-hand side. It involves the initial conditions. So the inverse transform of this will be what solution to this problem? The homogeneous problem, all right? So anything that does not depend on G immediately will give you the homogeneous solution. So this will be actually a particular solution, okay? And the particular solution to this problem, you can immediately see it's a convolution of G of t with a sine of 2t. Can you see that? It's a convolution of G of t with a sine of 2t, all right? So, and there is the answer, right? So basically, we have the solution to the homogeneous problem that involves sines and cosines. I mean, expected, right? The differential equation was y double prime plus y. And then we have a convolution of the sines with G, all right? And that's the final answer to this problem. All right, but I want to go a little bit further on this problem. If I can find, I only need one slide to actually do this. So let me call the homogeneous part phi of s, and the non-homogeneous, the Laplace transform the particular solution psi of s, okay? All right. So psi of s is g of s divided by s squared plus 4, all right? And this s squared plus 4 really came from the differential equation, okay? It completely depends on the left-hand side of the differential equation. Now, so let me concentrate on psi of s, okay? I'm going to concentrate on, where is it? I am going to concentrate on psi of s. So take a particular problem that g of s is equal to 1. All right? Let's take a very specific problem where g of s equal to 1. Can you remind me if g of s equal to 1, what is g of t? We saw it earlier in the lecture today. If g of s is equal to 1, what is g of t? It's a delta function, delta t, okay? So in that case, when I compute the inverse transform of psi of s, which is 1 divided by s squared plus 4, what do I get? What response I get to the system? How do we call that? You told me that if g equal to 1, all right, g of t is g of t is a delta function, delta of t. So what is the response to a delta function as a forcing term? How do we call that? Impulse response. So basically, what we're getting here, if g equal to 1, this thing will give us the impulse response. All right? So this is significant. Okay? So basically, if g is equal to 1, the problem that we are solving in computing this, inverting this h of s, basically, is solving this problem, which is the impulse response. All right? So can somebody tell me now? So remember that this particular solution was the product of h of s, which is 1 over square plus 4, that depends on the differential equation, times g of s, and g can be any forcing term, all right? G can be any forcing term. So can you tell me how I can use the impulse response, all right? How I can use the impulse response to write the response to any forcing term g of t. Remember, you told me that if g is equal to 1, the function that you get corresponding to this capital H is the impulse response. So H is the impulse response. So then what is the function corresponding to H times g for any g? Is the convolution of g with what? You remember when we have the product of two Laplace transforms, the function corresponding to that is the convolution of the two corresponding functions. Now, you also told me that h of s alone corresponds to the impulse response. So h times g then is the convolution of what? Of g with, and h is what? What did we say? We just proved that h is? It's the impulse response. So basically, the solution, a particular solution in the homogeneous problem, it's nothing else but a convolution of the impulse response with the external forcing term g of t. So basically, if I can only find it somewhere, because there are two examples in the notes on exactly the same problem, this is what we have. The particular solution, basically, it's a convolution of the impulse response with the forcing function that you have. And you remember, I used this before. So if actually, if let's say your forcing function is a step function, can you actually see that the response to the step function is the integral of the impulse response? You remember that? The response to a step function is the integral to the impulse response. The proof is there. And the response to any function is the convolution with the impulse response. And actually, if you look at that integral, right, it makes sense because when you apply this function g of t, you can think that instantaneously you apply an impulse. All right? So you're saying at any time down here, compute the effect of each previous impulse, all right? And the effect of each previous impulse is nothing else but h at t minus tau. So if I have an impulse at tau, its effect at t minus tau will be h of t minus tau. So effectively, you know, I am convoluting all this together. I'm adding all of these results, and the response at time t is this nice convolution that you see here. So this is very important. I see the time is 11:24. The light will turn off. So have a good weekend, and I will see you on Monday with something completely different.